Okay, last time we were working on this generic path search algorithm, and we were fleshing it out in a couple of different ways. The main thing that we did was to improve the algorithm by making sure that we don't explore redundant paths. So we added this explored node to make sure that we don't add a node to the frontier if it's already been added before. But we were left with this dilemma of selecting a path from the frontier when there are multiple possible paths to choose from. So that's the topic of this video. And for now, we're going to consider just the simplest possible ways of resolving this. So we're just going to be thinking in terms of sort of a fixed policy based on the order in which the paths were added to the frontier in the first place. And there are really sort of two reasonable ways we might do that. One is to turn it into a depth-first search. And if you remember from your data structures course, if you want to traverse, say, a tree in a depth-first way, the one way of doing that is to use a stack to maintain your position in that tree. And that's what we're going to do here. So I've, again, highlighted in blue what's changed. And the frontier now isn't a set, it's a stack. So every time we put a path onto the frontier, when it's time to decide which path comes off the frontier, well, it's going to be the one that was most recently added. So let's work through this. We're going to need a slightly more complicated example to sort of see the implications. So let me draw a slightly more complicated graph. Say something like this. A grid of states. It's good enough for now. And we'll say that there are arcs connecting all of these adjacent states. And I'm not drawing any arrows here, so we can assume that that means that there are arrows in both directions. And we'll just call that the start state. So we won't think too much about where the goal state is right now. All right, so let's just start this new version of the algorithm. And for the sake of concreteness, right, we'll say that when we're adding nodes to the frontier, we add in order from left to right. So how do things get started? Things get started in the same way that they did before. So we'll indicate with blue which nodes are in the frontier. So initially, this node is added to the frontier. Okay, we get to this point, we pop it off, so nothing has changed now. There's only one element anyway. So he's removed from the frontier, and he's added to the explored set. So let's indicate the explored set with green. Not in the frontier anymore, now he's explored. And we're going to add all of the paths that are reachable from that node that was just removed from the frontier. So in this case, right, that's this node, he's on the frontier, this node is on the frontier, and this node is on the frontier. And notice I added them in the order left, top, right, so we're moving from left to right, which means that when it comes time to remove the next path from the frontier, this is the candidate that's going to be chosen because it was the last one added and we're dealing with a stack. So if we keep the algorithm going, this node is removed from the frontier and added to the explored set. At this point, it's time to add his neighbors to the frontier. Notice that this node will not be added because it's already in the explored set, so this check fails. But this one will be added, so this node becomes blue. And now it's time to move through the loop again, and right, these guys are stuck here. They're going to be sitting there for a while. This was the most recently added node in the frontier, so that's going to be the one selected. It becomes green. And now it's time to add its neighbors to the frontier. And this is where that frontier check comes into play, right? This isn't in the explored set yet because it hasn't been expanded, it hasn't been selected. But it is in the frontier, so we don't want to put another version of it in the frontier, another copy of it in the frontier. So we don't. So the only node that passes the check is this one. So that's the one that's going to be picked. It's going to turn green. Maybe I should have made the graph a little bit bigger. I don't get the point of what's going to happen here. he's going to be picked. Both of his neighbors will be added to the frontier. This is the most recently one added. He's going to be picked. And you can see where this is going, right? This search is just going to rocket up along the right side of this graph, which maybe is okay. Maybe the goal is up here somewhere. But if it turns out that the goal was here, maybe this stack-based approach, this depth-first search-based approach isn't the best idea, right? So that's what happens in a depth-first search. You just rocket off, and you don't necessarily visit nodes that are near your start nodes early on in the search. So whether or not that's a good thing depends on where the goal actually is. But it does mean, right, we will eventually get back to this node, and we'll eventually get back to this node, so these will be reached eventually, but the path that we choose may not be the shortest path. So depth-first search has some problems, right? One, it explores potentially long, the main problem is that it explores potentially long paths before it explores short paths. So we probably, in many cases, we don't want to use depth-first search. Well, what's the alternative? Hopefully you can see that the alternative is to use a breadth-first search, right? So explore all of the nodes that are near our start state before we explored any of the nodes that are further away. And the change to the algorithm that makes that possible is very simple. We just replace this frontier. Instead of it being a stack, we make it a queue, right? If we think back to what would have happened in this algorithm then, right, after this node was this would have been the first node expanded, right, this one here. That would have been followed by this node, which would have been followed by this node, and we wouldn't expand any of those nodes that were added when these were being expanded until we dealt with all of the nodes that were expanded that were added on the first step. So I'll let you, maybe we'll work through some examples of that in class, and that's so I guess that also raises the question of why even talk about depth-first search? Why did I introduce depth-first search first when it looks like it's the dumb approach? And it turns out that there is at least one advantage, which is that the frontier stays relatively small, right? So if we sort of had traced this up through thousands of nodes, that frontier is sort of growing, linearly with the length of that path. In contrast, breadth-first search, right, works out in that queue gets wider and wider and wider, and the size of that queue can grow exponentially. So breadth-first search is much more space expensive than depth-first search is. Of course, throughout all of this, we haven't been dealing with the possibility that these nodes have costs associated with them. If that's the case, right, I said that breadth-first search is guaranteed to find the shortest path to the goal, but that isn't the case if we want the shortest path in terms of cost. So that's what we're going to have to talk about in the future, and we'll talk about that next time.